Okay, my name's Stephen Haunts and welcome to my talk on .NET Data Security, Hope is Not a Strategy. So just a little bit about me. So most of my time is spent these days doing work for Pluralsight. So I've produced 12 courses that are published now and I've got 13th due out soon. I also do a lot of travelling around doing training, around cryptography training in .NET is one of the courses I'm running at the minute, and I've also run a workshop for the last 2 days here doing that subject. And I've also been doing some work with a payments company in the UK called LadderPay. I'm also an author, so I write a lot of books. I've got 3 out at the moment on various different software development subjects, and I've got loads more coming out. So that's the hard sell done. So we're going to cover quite a lot of ground quite quickly today when we talk about cryptography in .NET. So I just want to show you some other resources that you can refer to afterwards if it's a subject that interests you. So I've got a course on Pluralsight called Practical Cryptography in .NET, which kind of talks about what we're going through today, but it goes through it a lot slower and works through a lot more examples. Another course that people may find interesting is one I've done here with Lars Klint, which is all about how to use Azure Key Vault in Microsoft Azure, which you might find interesting. Also, at the GitHub address there, I've got all the source code for that course. So even if you're not a Pluralsight subscriber, I've open sourced all the code, so feel free to go in and take it, because it kind of follows what we're talking about today. And I also have a copy of these slides available on GitHub as well, if you want to grab them. Okay, so why are we here? So I go around doing this talk because I believe that everyone as developers has a responsibility to their company to help protect their data. So is everyone a developer in this room? Pretty much most of you. You're all .NET developers? A few, that's good. Typically, a lot of companies take a very blasé approach to security and data security, and they keep their fingers crossed and hope it's not going to happen to them. And they literally do think that hope is not a strategy. I've worked with lots of companies that have taken this approach, and it is wrong. Stamp to projector, okay? The projector's going to play nicely today, is it? So yeah, so a lot of them go with the idea that hope is not a strategy, and certainly in my experience, when I've worked on a lot of projects, this is generally what seems to happen. A lot of the cool security stuff that we want to put in to protect data normally gets pushed to the back of the project because people only care about features and don't necessarily think of security as a feature. So what this talk isn't, so we're not going to go deep down into the underlying algorithms like AES and DES. We're not going to look at how they work internally because an hour wouldn't be long enough to do that. And we're not going to talk about cryptanalysis, the art and science of breaking codes. That's not what this talk's about. So what this talk is about is people like me and you who sit there every day for our organisations writing code and delivering code into production. So when I first started delivering this talk, it was very much centred around what we now class as the traditional .NET framework. And when .NET Core first came along, all the way up to .NET Core 1.1 and .NET Standard 1.6, most of the crypto libraries in the framework weren't available to us, so we couldn't really use .NET Core, which is a bit of a problem. But last August, Microsoft very kindly released .NET Core 2 and .NET Standard 2, which now includes the majority of the APIs that we want to talk about today, which are also in the .NET framework, so we can now have some cross-platform ability with our code. So whilst today we're going to be mostly looking at the Microsoft APIs and how they work at sort of a higher level, the actual broad concepts of what we're discussing is kind of universal. So if you're a Ruby programmer or a Java programmer, the actual concept of what we're talking about is transferable. It's just we're looking at one particular set of APIs. But the actual idea of what we're talking about is kind of universal. So this is what we're going to cover. So we're going to start off by looking at random numbers, because it's kind of the core principle of cryptography, so have good random numbers. We're then going to take a quick look at hashing and HashMessage authentication codes. We're then going to talk a bit about secure password storage. Then we're going to talk about symmetric encryption and AES in particular. And we're going to talk about asymmetric encryption and RSA in particular. And then we're going to talk a bit about digital signatures. But then once we've done that, we're going to combine some of these things together to do what's called hybrid encryption. So what is cryptography? This is probably a silly question to ask at a security event. But cryptography is generally regarded about protecting information, and we do that by encryption. And to do encryption, we have to use encryption keys, whether they be asymmetric or symmetric keys. And the result of an encryption process is commonly referred to as ciphertext, and the art of breaking the ciphertext to recover the plain text is known as cryptanalysis. But it's kind of more to cryptography than just encryption. So cryptography kind of splits down into four main pillars. So we have confidentiality, and this is what we traditionally think of when it comes to cryptography. We have integrity, which is about making sure that something hasn't changed or broken when it's in transit. We have authentication, which is about proving whether someone's actually allowed to do an operation or not. And then we have non-repudiation, which is proving that you were the person that sent the message. It's a bit like having someone witness signing a contract. It's a good way of thinking about it. And we're going to cover all four of those in this talk. So cryptography is used everywhere. I'm sure everyone in this room knows that. We're at NDC Security. I mean, you cannot literally, you cannot wake up in the morning without some kind of cryptography happening. As soon as you turn your phone on, your TV, your computer, you do online shopping, taking money out of a cash machine. There's a cryptographic handshake between the ATM and the bank. The newer cryptocurrencies, which are very popular at the moment, and even modern voting machines and some of the new blockchain-based voting machines are all based around cryptography. Okay, so let's start off by looking at random numbers. So random numbers are absolutely pivotal to everything we do when it comes to cryptography. Whether we're using .NET, Ruby, Java, a good set of random numbers is very important for it to be able to generate. So the one thing you don't want to use is system.random. So system.random is great for doing, simulated dice throws or generating lottery numbers, but it's deterministic. So if you pass the same seed into the random function, you'll get the same numbers out. So for cryptography, it's completely useless, and it's also not type safe. So the one we should be using, and that's a lot better to use, is the RNG Crypto Service Provider class, which lives in system.security.cryptography. And thankfully, it's very easy to use. Everything in .NET is very easy to use, which is great. So we have a method here, generate random number, and we pass in a length, which is a length in bytes. We initialize the RNG Crypto Service Provider. We create a new byte array at our desired length. We call getBytes on the random number generator object, and we return the result. So what we get back is a byte array of random data. So the next thing I want to quickly look at then is hashing. So hashing can most commonly be thought of as being like a digital fingerprint for a piece of data. So you pass some data in, you hash it, and you get this kind of unique ID fingerprint or piece of data out the other side. Now hashing should have four core principles behind it, or four core tenets. So one, it should be easy to compute. So if I've got a file, a string, a piece of data in a database, it should be easy to compute the hash. It should also be infeasible to generate a specific hash. So you shouldn't be able to start off with a hash and say, what data do I need to generate that hash? You shouldn't be able to go in that direction. It should be infeasible to modify a message without changing the hash. So if you have a big long string that you want to create a hash of, and you then go and change one character, you'd expect the entire hash message to be completely different, not just a little bit. And it should technically be infeasible to find two identical hashes. This is what's referred to as a hash collision. So one of the principles of a good hashing function is we don't want to have hash collisions. Now hashing is a one-way operation, and I've compared it to encryption on there, which is a two-way operation. So with encryption, you use a key to encrypt and decrypt your data, so you go both ways. But in hashing, you only go one way, or you should only be able to go one way. So there's various different hashing algorithms available to us in the .NET framework. So one of them is MD5, and this produces a 16-byte hash value. And it was designed by Ron Rivest in 1991. But there was a problem found with it initially in 1996, where they found a hash collision resistant vulnerability. So if you're creating new software, you don't really want to be using MD5, but I include it in the talk because if you're working with lots of legacy systems, like I used to work for a bank and we had AS400 mainframes running our core banking platform, it was quite often we'd have to do MD5 integrity checks against data coming back from that, because that's what that platform used. So it is still useful to know about it for legacy purposes. Next up we have the secure hash family. So the first one is SHA-1, and that produces a 160-bit hash value. Then we have SHA-2, which commonly returns 256 bits and 512-bit hashes. And then there's a new one called SHA-3, which currently isn't in the .NET framework. I'm not sure when it's come in, but this was designed specifically to be a hashing function which didn't have any involvement by the National Security Agency in the US, whereas all the other ones had involvement of the NSA. So in this day and age, that makes people a bit nervous. So a new variety was found through a competition. So if we look at how to use SHA-256, they've all got very similar interfaces. So once you know how to use one, you know how to use them all. But it's very easy to use. So we use a method here called compute hash SHA-256. We pass in a byte array, which is an array of the data that we want to hash. So if it's a string, you'll need to encode that into a byte array first. We call the static method create on the SHA-256 object, and then we call compute hash by passing in our data, and then we receive the hash data back out as a byte array. Bless you. So the next one we want to look at is authenticated hashing, which kind of builds on the concept of hashing. And the key difference with an authenticated hash is, as well as passing in a message, we also pass in an encryption key or a key. So in this case, we could use a 32-byte key that we pass in. And what this means is that if anyone on a receiving end of a system wants to recalculate the same hash, they have to be in possession of that key to recalculate the hash. If they have a different key, then they'll get a completely different hash off the back of it. So it's a good way of being able to authenticate or prove who it was that sent a hash. So not only does it give you integrity checking like you do with normal hashing functions, it gives you authentication as well. Now, HMACS in .NET can be based on MD5 and the SHA family. The examples we're going to look at will be based on SHA-256. And the strength of the hashing is dependent on the length of the key. So 32 bytes, 256 bits is probably a good minimum to use these days. And the most common attack against this type of hashing is a brute force attack, which we'll look at in a moment. So again, very easy to use. So we have our little sample method here. We pass in a byte array of the data that we want to hash. We pass in a byte array which represents our key. That could be 32 bytes. We then construct the HMAC SHA-256 objects whilst passing in the key. And then we simply call compute hash, passing in the data we want hash, and then we receive a byte array back out the other side. Okay, so now I want to talk a bit about secure password storage. So whether we like it or not, passwords are still one of the most common ways in which people can authenticate themselves on systems, because they are generally easy for our users to remember. And hashing is one of the most common ways of doing that traditionally. So has anyone worked on a system where you've just created and stored a hash of a password, a SHA-256 hash? It's okay to admit it, I've done it as well. Now there's two common attacks you can do against this. So you can do a brute force attack where you just keep on trying lots of combinations until you manage to crack the password, or you can use a dictionary attack. And these dictionaries typically are gigabytes in size, and you use tools like HashCat to be able to break the password. In the workshop the other day we did a HashCat demo, and all of us running it managed to warm the room up quite nicely as our machines nearly melted. So there's a good example of how to break them here. So this is a website called crackstation.net, and it just makes for a good example. So you pass in a SHA-256 hash up there, type in the captcha, hit crack hashes, and it's worked out that it's a SHA-256 hash and the password was secret69. So that's just a kind of a trivial example that shows you how easy it is. So storing hashes on their own is probably not a great way of storing passwords. So the next best thing to that is storing what's called a salted password. And what this is you append some data onto the end of the password before you hash it. So again, that could be a 32-byte random number that we've generated with RNG crypto service provider. And once you've concatenated those two together, you just hash it as normal. So does anyone do this in their current systems? So a few more people, I've done that as well. And no, generally that's pretty good. If you've got a 32-byte 256 bits piece of entropy on the end of the password, that's going to be quite difficult to break. But who knows what's going to happen in 2, 3, 4, or 5 years or more. Tools like HashCat use GPUs for breaking passwords, and they're only getting faster every year. So what might be secure today might not be secure in a few years' time. So what we want to do is we want to stop Moore's law and the evolution of graphics cards and tools like HashCat being a problem. So the next best thing we can use is what's called a password-based key derivation function, or a PBKDF2 for its fun name. And conceptually this is very similar to what we've just done. So we have our password we want to hash, we have a salt that we pass in, so again that could be 32 bytes of entropy that we've generated. But then we have this number of iterations, and what this is it's a number of times which that hashing function is going to get run internally to generate our password. And the reason we do this is we want to algorithmically slow down the hashing process. So instead of HashCap being able to do billions of combinations per second, you might be able to reduce it down to, say, 10 combinations per second. So in .NET, again, this is very easy to do. We have a very nice method in the framework called RFC2898 derived bytes. It does what it says on the tin. So we have our hash password method that we've written. We have a byte array of the data we want to hash. We have a byte array of our salt. And then we pass in a number of iterations. And then we just pass those into RFC2898 derived bytes. Call getBytes 20 because it uses SHA-1 internally, so it only returns 20 bytes. And then we return the result as a byte array. Now I did some timing tests on this. So on the left column we have the number of iterations, and then we have a time in milliseconds on the right, and then I've correlated that onto a graph. So as you can see, there's a linear correlation between time and the number of seconds. So for 100 iterations it took 2 milliseconds, all the way up to 500,000 iterations, which took around 7 seconds. So the reason I show this is if you're going to incorporate something like this into your systems, you need to think about the trade-off in performance. So what is an acceptable level of time to wait for a password to be hashed? So if you're having a person authenticate onto a system, is having them wait 2 seconds once they've typed their password acceptable? It might be to your company or it might not. So you have to think about the trade-offs in time. So is everyone familiar with this company here? So they badge themselves as a dating agency aimed at people that want to have affairs. So they had a massive data breach a few years ago. I'm sure everyone in here has heard of it, haven't they? It was quite a big deal. So they had lots of their data stolen and their source code stolen, and a lot of the hackers wanted to go after the passwords. So they looked at how the passwords are being stored, and they would be using something called bcrypt, which is very similar to our password-based key derivation function. So actually what they were doing was quite good. They were doing iterated hashing to slow down the hashing process. That's quite cool. But then what they also found when they did when they went through the source code is that some unwitting software engineer had obviously tried to optimize the logon performance of their system. So once you successfully logged on, it was storing MD5 tokens locally of the password to speed up the process. And then once they found this out by looking at the source code, obviously they then managed to go off and recover the vast majority of the password file. So there's a really good article on Ars Technica about it, at that link there. It makes for fascinating reading. Okay, so let's move on to encryption. So we'll start off with symmetric encryption. So what this involves then is you have a piece of data, you encrypt it with an encryption key, and then you decrypt it using the same key. That's why it's symmetric. But there's a problem with symmetric encryption, and that is that sharing keys is hard. So if I generate a 32-byte encryption key, and I want to send one of you some data, how do I get that key to you? Do I email it? Probably not a good idea. Stick it on a text file on the server somewhere? Again, not a good idea. Probably don't want to stick it in a database. So unless you're actually physically in the room with me and I hand you a key with it on, it's probably not going to be very good. So again, just to illustrate the point that we were saying before, so hashing is a one-way process and encryption is a two-way process. So we're using that same key to recover our information. So symmetric encryption works by splitting your data down into blocks, and then it encrypts several blocks at a time and does lots of swapping operations internally. So on computers, things like AES are actually very efficient to run. And in .NET we have 3 options which are quite common to use. So we have DES, which is the original data encryption standard, we have triple DES, and then we have the AES crypto service provider. And they all inherit from a common base class, which is symmetric algorithm. So once you know how to use one, the interfaces between all 3 are actually pretty much the same. Again, I mentioned DES and triple DES on here, not because you'd want to use them for a brand new system, but if you are integrating with old legacy systems, then the chances are you might have to decrypt something that has been encrypted with DES or triple DES. So AES stands for the Advanced Encryption Standard, and it became a standard by the National Institutes of Standards and Technology back in 2001. And it's invented by 2 mathematicians, Joan Damon and Vincent Ryman, and it was based on their original cipher, which is called the Rindell cipher, and that Rindell cipher was what won the competition and became the standard. So we have a choice of 3 keys we can use with AES. We have 128 bits, 192 and 256 bits. Whenever I use it, I've always just gone straight to 256 bits. As well as passing in the key, we have what's called an initialization vector. So for some of the encryption modes in AES, you have to pass in an additional 16 bytes, which it uses to encrypt the first block. The initialization vector doesn't have to be kept secret. You can send it along with the encrypted message. And we also pass in the plain text, so that's the data that we want to encrypt. So it could be, a string, a byte array, a file that's been serialized. We run that through AES with the key, and then we get our ciphertext back out the other side. Now in .NET, we have a choice of 2 versions of this that we can use. So we have AES Managed and AES Crypto Service Provider. Now fundamentally, they're both doing the same thing, but AES Managed is a native .NET implementation, whereas AES Crypto Service Provider uses the underlying Windows crypto platform. Now, even though AES manages a native implementation, it's not certified by FIPS, so it hasn't got the FIPS 197-2 certification, whereas AES Crypto Service Provider has. And what that means is that if it's certified, if I go and encrypt something in .NET and then pass that data off to a system that's written in Java, for example, if their AES implementation is also FIPS certified, I'm going to have a good level of compatibility between the two. That doesn't mean that AES Managed doesn't work, it just means it hasn't been certified. So an example of using AES, so if we want to encrypt some data, we have our encrypt method, and we pass in a byte array of the data we want to encrypt, a byte array of our key, so 32 bytes in this case, and our initialization vector, which again is 16 bytes. So we create the AES Crypto Service Provider object, we assign the key in the initialization vector, and then we create a memory stream and a crypto stream, because AES is stream based in .NET. And over here we have something called AES Create Encryptor, which we set. So you write the data into the stream, you flush it, convert it back to an array, and then you have your data encrypted. So to go the other way, it's very similar. So it looks almost the same, except the only difference is instead of create encryptor, we pass in create decryptor into the crypto stream. We pass our key and our initialization vector, as we did before, pass in the encrypted data, and then that stream will decrypt our data for us. So that's symmetric encryption. What I want to look at now quickly is asymmetric encryption. So one of the most common ones which you can use is RSA, which is what we're going to look at today in our example. And this uses a concept of public and private keys. So instead of having just a single key for encrypting and decrypting our data, like we did with AES, with asymmetric encryption we have 2 keys, and those keys are those 2 keys are mathematically linked. And I'll show you an example of what that means in a moment. So RSA was developed by RSA Data Security Incorporated in the States by 3 guys, Rives, Shamir and Edelman. So RSA is an acronym of their names. And the way that RSA works is that there's no efficient way to factor very large prime numbers. So if you have a huge prime number, it's very hard to work out what the 2 primes are that you multiply together to make that resulting prime. And that's kind of how what the security is based on with RSA. So these prime numbers are huge, they're like thousands of digits long. So 2048-bit keys is the current recommended minimum length, but you can go up to 4096-bit keys as well. And there's 1024 bits, but you really don't want to use that anymore. Okay, so if we look at what makes up the key, so I was talking about multiplications of primes. So if I was to say to you, what is 23 times 17, those are 2 prime numbers, then the answer is 391. You can work that out very easily, either in your head or on a calculator. But if I was to say what prime numbers do you need to multiply together to make 5,963? Does anyone know who wasn't in my workshop? So it's harder to do, isn't it? So now if you imagine, instead of 4 digits, that's like hundreds or thousands of digits long. That's a very tough problem for a computer to solve, and that's where the security of RSA comes in. So the actual answer is 67 times 89. So if we think about this in terms of keys, so our public key is the resulting prime, so the 5963, and our private key is 67 times 89, or the two numbers 67 and 89. Now there's more stuff that goes into the keys than that, but the basic premise is around these prime numbers. So the way RSA works is, if I want to send some data to one of you, now you have your own key pair, you have your own public and private key. The private key is private, you keep that safe, you don't let anyone else know it. But your public key, you can let anyone else know it. So you can put it on your website, you can email it to people, you can hand it to someone. So if I want to send you some data, I encrypt the data using your public key, and then you decrypt it using your private key, because only you know that. Then if you wanted to send something back to me, you get my public key, encrypt it with that public key, send me the data, then I decrypt it with my private key. So if we look in .NET about how you can generate the keys, so we have a class called RSA Crypto Service Provider, and we pass in the key length into the constructor, and then we can just call export parameters with false to give us our public key, and export parameters true to give us our private key. So in this example here, I'm just storing them as two local memory variables, but in the RSA implementation you can export those to an XML file if you so wanted to, or you can store it in the Windows crypto service container. Okay, so to encrypt some data, we have our encrypt method, and we pass in our data, again as a byte array. And then we construct the crypto service provider object again, passing in the length of the key we want. We import our public key, and then we just call rsa.encrypt, passing in that data, and then again we get a byte array back out the other side. To decrypt, it's fairly similar. So we pass in our data as a byte array, construct the object, import the private key this time, because we're decrypting the information, then call rsa.decrypt, and then we get the original plain text back out the other side. Now there is a limitation with RSA, so you can't encrypt more than the size of the key length. So if you've got a 2048-bit key, you can't encrypt more data than that key, which is one of the limitations because it's based on modulus arithmetic. So one thing you might be thinking is, well, if I've got a very large piece of data, I could chop it up into chunks and encrypt those individually, which you can do. There's nothing stopping you from doing that, but it is very inefficient and very slow. So we'll look at some techniques for what we want to do instead in a moment or a bit later. Okay, so the last primitive that we had on our list is digital signatures. So digital signatures are used for being able to sign some data so that you can prove the authenticity of that data. Now a digital signature has three components to it. So we have key generation, we have a signing algorithm, and then we have a signature verification method. And the way it works is if you have a large piece of data, say, I don't know, a file, you generate a hash or a HashMAC of that data, and then you create a digital signature of that hash. Because internally in .NET our digital signature is based on RSA, so we have the same key length limitations. So we don't create the signature of the data itself, we create the signature of a hash of that data. So has anyone used websites like DocuSign or anything similar before? Just one person. Okay, so it's a good analogy of what digital signatures are about. So DocuSign is a service where you can upload an actual contract, so like a job contract, for example. You write your name and various bits on the contract, and then it will create a hash of that data and digitally sign that contract. So it's kind of like an equivalent of having someone witness you signing that document. So if later on you're ever in court and you're trying to deny that you ever signed that contract, or you want to deny that you put certain data in that contract, you can't deny it because it's been signed with your keys. So if we look at my amazing piece of artwork to try and describe this. So we have Bob, who wants to send a digital signature. So what he does is he uses his private key to sign his hash. So if you remember back to RSA, when we encrypted, we used our public key. But in this case, the sender is using his private key to sign the message, because only he can sign it with his key. So he sends it over the internet down to Alice at the bottom there, and she uses Bob's public key to verify the signature. So that means that she'll get a response back saying whether it was indeed Bob's private key which signed that piece of data. So again, very straightforward to use. So to generate our key pair for a digital signature, it's exactly the same as what we did for RSA. So we construct the RSA crypto service provider class, telling it what key length we want, and then we just export our public and private key. So in this example again, we're storing it as just two member variables. To sign some data, we have to use this really nicely worded class down here called the RSA PKCS1 signature formatter. Just rolls off the tongue, doesn't it? So we have our sign data method, and we pass in a byte array of our hash of the data that we want to sign. Because again, remember, we can't sign the entire document, we're signing the hash of it. We import our private key, because to sign the data we have to use our private key. We construct the RSA PKCS1 signature formatter. We tell it what hashing algorithm we're using, so in our case SHA-256. And then we call create signature, and then that returns us a byte array of that digital signature. So then to verify what we have, or to verify that digital signature, we pass in the hash of the data that we want to sign, the original hash. We pass in the byte array of the digital signature that was created. Construct the RSA object, import the public key this time, because remember we need to use a public key to verify the signature. And this time we create the RSA PKCS1 signature deformatter, obviously. And then we set the hash algorithm to SHA-256, and then we just call verify signature, passing in the hash of the data and the original signature that was generated. If it's valid, you get true returned. If it's invalid, you get false returned. So if it's false, then you don't trust the hash of that data or the signature. Okay, so we've gone very quickly through some of the primitives that we've got in .NET. So if we do a quick recap. So we talked about the idea of confidentiality, and to do that we use AES and RSA because they're our encryption protocols or encryption primitives. For integrity, the ability for us to detect whether something's changed over time or not, we looked at various different hashing algorithms, but we've been using mostly SHA-256. For authentication, so where we want to be able to prove that it was someone that actually generated that hash, by using a key, we used a HashMAC and we used a SHA-256 variant in our example. And then for non-repudiation, which is where we don't want people to be able to deny having signed some data or signed a contract, we've just looked at digital signatures. So those are some of our base primitives that are available to us in .NET. So what I want to look at now is how we can combine some of those together to do what's called hybrid encryption. Okay, so we mentioned before that RSA has some limits on the amount of data that you can encrypt in one go. And we also want the flexibility and the speed and efficiency of AES, but the problem we have with that is that exchanging a key between two people is very hard. So what we're going to look at first of all is how we can combine RSA and AES together so that we can get the benefits of both. So in our example here, we have an AES session key that we generated, so that's a 32-byte key. We generate our initialization vector, which is 16 bytes. And then we encrypt our data using that session key and initialization vector, just exactly what we've looked at earlier. But then what we do is we use our recipient's public key and we encrypt that session key. So we're encrypting that AES key. We send that encrypted data and the encrypted key over to our recipient. First of all, they have to recover that AES key, so they decrypt it with RSA using their private key. And once they've recovered that encryption key, they can then use AES to decrypt the data. So if we were thinking of it as stuff that we store in a database or a packet of data, this is what it would look like. So we have our RSA encrypted session key. We have our AES initialization vector, so it doesn't have to be encrypted, it can go in the clear. And we have the AES encrypted data. So let's run through that as another example. So we've got Alice again generates her key. She generates her initialization vector, 16 bytes. She encrypts her data with AES. Then she uses Bob's public key and RSA to encrypt that AES key. And then she sends that all over to Bob so he can read it. So when he receives that data, he uses his private key to decrypt that AES key, so he's recovered the key. And then using that recovered key and initialization vector, which has just been sent, he uses AES to decrypt the message. So he gets a message, meet me at noon below the clock tower, wear a red rose in your button. Great, so now he wants to send a message back to Alice. So he generates a new key, because you never reuse keys, you always generate brand new ones. So he generates a new session key, 32 bytes. He generates a new initialization vector, which is 16 bytes. Then using AES, he encrypts his message, and then using Alice's public key, he encrypts that AES key, so that key is now encrypted. And then he sends a message back over to Alice. So then she uses her private key, this time, to recover that session key. Then with that session key and her initialization vector, she uses AES to decrypt the message. And she says, I will meet you, I will be wearing a blue hat and red boots, because she's very fashionable. So if you think about what we've done there then, so we said we had the problem with AES, where it's very difficult to send or share keys between people. But AES is quite fast and efficient, because it's very algorithmic in how it works. But then we've got AES, which has keys that are split, so it makes it very easy for us to then use RSA to encrypt our other key, which is hard to send. So we're actually getting the benefit of both of those protocols together. So let's build on that a bit more and add integrity to it. So this diagram is virtually identical to what we had before. So we have our session key. We encrypt our data with that session key. We encrypt the session key with the recipient's public key. And then I take a HashMAC of the ciphertext and the initialization vector combined. And because I'm doing a HashMAC, I need to give it a key. So I use the session key, which I still have an unencrypted copy of. So that gets sent over to the recipient. They use RSA to recover the private key. They use RSA to recover their AES key using their private key. Once they've recovered that key, they regenerate the HashMAC of the ciphertext and the initialization vector, because they've now got the key to pass into the HashMAC. If the hash is matched, then they can trust that the data has made it to them without being changed. So they can then go and decrypt the data using AES, and they get the message back. If that HashMAC is different to the one that was sent to them, they just disregard the message, because something's changed, so you don't trust it. So if you think about the data that's been sent, again, so we have the RSA encrypted session key, the initialization vector, the encrypted data, and we also send the HashMAC of the encrypted data. So there's 4 bits that we're sending. So let's extend that a bit further. So we've added integrity and authentication, because to calculate the hash, they need to use the key, but they need to be able to recover that key, so that gives us authentication as well as integrity. So let's now add non-repudiation. So again, very similar to what we had before. We generate our session key, we generate the initialization vector, encrypt our data with that session key, and then we encrypt that session key with the recipient's public key. So that's exactly the same. Then again, we calculate the HashMAC of the ciphertext and the initialization vector using that session key that we generated. So that's exactly the same as what we've just looked at a minute ago. But then the extra step is we create a digital signature of that HashMAC using our private key. So we've encrypted the key using the recipient's public key, because that's the encryption process with RSA. But to create the digital signature, I've used my private key. So that means then, on the other side, when they receive that data, they first have to recover that AES key using their private key and RSA. They then recalculate the HashMAC, because they've now recovered that key, so they can recalculate the hash. If the hash is matched, great, we trust the data that's been sent. If it doesn't match, we disregard the message, because it's been tampered with or changed in transit. But now, because we have that hash, we can then use the original sender's public key to verify the digital signature. So if that comes back as true, we know it was actually Alice that sent the message and not some other person. So again, if we look at the amount of data that we're sending there, so we have the RSA encrypted session key, we have the initialization vector, the encrypted data with AES, we have our HMAC with the encrypted data, and we have our digital signature. Now if you're writing a system that does this, I mean, you could either you'd be transferring that around in the database, you could serialize a lot of that stuff to JSON or XML when you're actually sending it between different people, because all the data in there is encrypted. Okay, so let's recap what we've done, because we've covered a lot of stuff very quickly there. So we started off by looking at random numbers, because they're absolutely pivotal to everything we want to do. You need good quality random numbers for symmetric encryption keys and for our HashMessage authentication codes. We've looked at various different hashing and HMAC algorithms, but the one we focused on was SHA-256 for the purpose of our example. We took a look at password storage, so we looked at various different methods of doing that. One we didn't cover is obviously storing passwords in the clear, but there wasn't really any point in including that one in the slides because we all know that's bad. But then we looked at hashing of passwords. So again, that's been quite a common technique that's been used for many years. But they're very easy to break by brute force or dictionary attacks using tools like Hashcat. So to make that slightly better, we then looked at doing salted hashes where you add additional entropy onto the password before you hash the password. So that could be a 32-byte random number that we've generated with our random number generator. And again, this is better. I think probably the vast majority of systems out there these days probably still use salted passwords. But the problem is, tools like Hashcat on very fast PCs with high-end graphics cards in there can test billions of combinations a second. So whilst they might be secure now, they might not be secure in, say, 2 or 5 years. So then we looked at how we can algorithmically slow down the hashing process for passwords. And for that we looked at password-based key derivation functions. And we use an object called RFC 9828 derived bytes, which is a very easy one to miss in the .NET framework because it doesn't really make much sense unless you know what it is beforehand. So from then we took a look at symmetric encryption. So we discussed briefly about DES, triple DES and AES, but the one we wanted to focus on for new code is AES. And AES is what's called a block cipher, and it's a symmetric block cipher, so you use the same key to encrypt and decrypt. But then we discussed that the actual problem with AES is that actually transferring those keys between people is very difficult to do securely. So then we looked at asymmetric encryption and we looked at RSA in our example. So RSA has pros and it has cons, so it is a very secure encryption algorithm, but it is quite slow because it's more mathematical in how it works. It's all based around modulus arithmetic as opposed to something more algorithmic like AES. But there are limits with RSA, so you can't encrypt data longer than the actual key size, so that's a particular downside, and it's quite slow. So after that, we took a very quick look at digital signatures, and we looked at classes like the RSA PKCS1 signature formatter and deformatter classes, which are brilliantly named objects. And what digital signatures give us is the ability to do non-repudiation of data. So if someone digitally signs something with their private key, they can't then go and deny having signed that data down the line. And digital signatures are actually valid in courts. Well, they certainly are in the UK. So if there's a contract dispute and you've used something like DocuSign, you can actually use the fact that that document has been digitally signed as evidence in court if there's ever a dispute. So once we looked at our primitives, we then looked at combining some of those together to do what's called hybrid encryption. So what we ended up with was a mechanism where we can use RSA to encrypt our symmetric encryption keys. So that gets us past the problem of securely moving those keys around. And then we built on that by adding some additional integrity using HashMAC, SHA-256 HashMAC, which also uses that encryption key that we generated. So that gave us some integrity and authentication when we send that message between two people. And then to finish that off, we use digital signatures to digitally sign the data that we're sending so that the receiver knows that it definitely came from a specific sender. So it's quite a lot in one go after lunch. I hope everyone's managed to follow through. So what next? So if it is something that interests you, then I have got a Pluralsight course on this. It's nearly 4 hours long, which goes through it a lot slower and has lots of worked examples. So treat this talk as, you know, the art of the possible. If it's something that you're interested in, then that course will probably be useful for you. Does everyone here use Pluralsight? Oh, brilliant, fair few of you. So that's on there, so you can just go and watch it. If you want to take things a bit further, and we did this in the workshop the other day, where we used the Azure Key Vault, which is a way of securely storing encryption keys in Azure. It uses hardware security modules behind the scenes to store those keys. So this course walks you through how to do that. So instead of locally storing RSA keys in certificates or whatnot, you can just store them in a protected key vault. If you want to play around with all the source code for everything we talked about today, I've got worked examples of the whole lot there. It's all under the MIT license, so you can just take it and do what you want with it. If it breaks, it's not my fault. But the examples go through each of the primitives, how they work with different tests, and then it works through the hybrid encryption example, so you can just use the code that's there for doing the hybrid encryption. So you don't have to think about it too much, you can just use it. The important thing is understanding how it works. These slides are on GitHub, on my repository in the conference talks repo, so if you want to grab the slides at all, there's a version of them there. And there's some books here which are very useful. So these are all books that I've personally enjoyed reading. If cryptography is something you are interested in, then I recommend these. The code book by Simon Singh is kind of a standard novel-sized book. It talks about the history of cryptography from sort of ancient times where it was all done on paper, right the way through to modern digital encryption techniques. The book in the middle, Everyday Cryptography, there's actually a new edition out of it now. It's got a white cover that was released towards the end of last year, but I've not read it yet, the new one. But the first half of the book talks about how a lot of these algorithms work internally, so it goes into quite a lot of detail, but it's not overly mathematical, it's quite easy to follow through. And then the second half of the book talks about some different practical applications, so like how TLS works, like the handshake on TLS, how cash machines do the handshake between, you know, the ATM and the bank. So it goes through lots of practical real-world examples. And then the book we have at the end there is Applied Cryptography. This is the book where back in the 90s the NSA tried to ban it, because back then cryptography was classed more as like a munition or a weapon. So there's very strict export regulations on cryptography. But this book goes into a lot of detail about how a lot of the older algorithms are built. It doesn't include AES because it was written before that. But if you want a really good mathematical explanation of how a lot of these different algorithms work, then that book is ideal to look at. So that's it. Thank you very much. You've got 10 minutes or so back in your diary to go get some coffee. So thank you very much.